So a logarithm is the inverse of an exponential function, and basically what it allows us to do is um, solve for exponents if we need to, right? So if I write log base b of a equals, the thing I'm trying to figure out is b to what power gives me a, right? B to what power gives me a? So b to what power equals a? So with that in mind, if I write like log base 10 of 100, you're trying to solve for the exponent such that 10 to what power makes 100, right? And so the answer to that would be 2. So log base 10 of 100 is 2. So with that in mind, any exponential function can be written, any logarithmic equation can be written in exponential form. So if I write log base b of a equals n, the equivalent exponential form of that is that b to the n equals a, right? All right, so natural log is just a special type of logarithm that's base e. So when we say log base e of x, we can equivalently say natural log of x. Oftentimes you'll hear scientists and mathematicians just call that log x. Like they'll verbally refer to this one as log x. Just it's so much more commonly used than any other type of logarithm. Sometimes you'll hear them refer to it as ln x to avoid the confusion. Okay. So if we say that natural log x equals y, we can use this same logic that any logarithmic function or equation can be rewritten in exponential form to say equivalently that e to the y equals x. All right, and so with that in mind, we can come up with some simple ideas about logarithms. If I'm asking you what's natural log of e to the x, well, then the thing you're trying to solve, remember, is the base to what power equals the argument. This thing is called the argument, the thing that you're taking the logarithm of. So the base to what power equals the argument? Well, the base of natural log is e. So I'm saying e to what power equals the argument? The argument in this case being e to the x. So e to what power equals e to the x? Well, the answer there is just x, which is why natural log of e to the x would just simplify to x. And in fact, natural log of e to any power just simplifies to that power, right? So if I do natural log of e to the third, that's going to be 3. Natural log of e, that's going to be 1, and so on. And likewise, if you this operation is called exponentiation. So if you exponentiate natural log by base e, you also get x. And that's just the idea that they're inverse functions, right? So when you compose inverse functions, you're just left with the input, which is x in this case. All right, and then on the bottom, I already went over why natural log of e is 1. Go ahead and give me a green check when you're done with this page, and we will move forward. All right, solve the equation e to the power of the quantity 5 minus 3x equals 10. So this is just like a pre-calc / algebra 2 problem. But it's probably been a while, so I just wanted to review how we would do this. So right? The idea is, because of those properties that I just showed you, I can take the natural log of both sides of this equation. Now, what is, on the left-hand side, natural log of e to the 5 minus 3x going to simplify to? In the chat, if you can. Good, exactly, 5 minus 3x. So I get 5 minus 3x equals natural log of 10, which is just its own constant, and we'll just treat it as a constant, right? So just leave it as natural log 10. Now, just a little algebra, subtract 5 from both sides, we get negative 3x equals natural log 10 minus 5. Divide out the negative 3. X equals natural log 10 minus 5 over the quantity negative 3. That's the exact answer. Unless they ask for an approximation, I wouldn't even bother putting this in the calculator. There's our answer. I mean, simplify if you can, but in this case, there's nothing to simplify really. So I just leave it as is. Any questions? Go ahead and give me a green check to indicate that you're ready to move on. Okay. Reminders of some other properties of logarithms that directly follow from properties of exponents. So I'm not going to prove all these. Maybe I'll prove one or two of them. But these are properties you should have learned in Algebra 2 and pre-calculus. The first one being log base b of x y is equal to log base b of x plus log base b of y. And I'll just real quick, I can prove this one pretty quickly for you. If you take log base b of x times y, so if I exponentiate both sides by b, which means I'm just having the right-hand side become the left-hand side become the exponent on b, and the right-hand side become the exponent on b. So exponentiation and logarithms are inverses of each other, and we just saw in the slide before the last one that when you do that, the logarithm and the exponent undo each other, or the exponential base undo each other, and I'm just left with x times y, the argument here. Now on the right-hand side, I have an addition going on in my exponents. The only time I add exponents is if I have a product of powers. So I can rewrite this as b to the log base b of x times b to the log base b of y. Right? Because if I had a product of powers like this, I would add the exponents like that to simplify it. All right, so now that I've done that, I can now separately use the idea that logarithms and exponentiation are inverse of each other. So b to the power log base b of x is just going to simplify to the argument x times b to the power log base b of y is just going to simplify to the argument y, and I end up with x times y equals x times y, which is an identity, and thus I have proved the formula. So I'm not going to prove the other two just for time's sake, but similar ideas. So log base b of x divided by y can be expanded to log base b of x minus log base b of y. And log base b of x to the r power can be rewritten as r times log base b of x. Again, this should be a review. You should have seen these properties at some point. So let's just practice that. Still not doing any calculus with this, just doing a few pre-calc things. So we want to express natural log a plus half natural log b as a single logarithm. So I'd rewrite that as natural log a plus natural log b to the half power. Right, so that third property says if we have a coefficient on the logarithm, it can come around and be an exponent on the argument, or vice versa. All right, and then the sum of two logarithms of the same base equals logarithm of the product of the arguments. So a times, and I'm just going to write b to the 1/2 as root b. And there we go. All right, moving on from there. The derivative of natural log x is 1 over x. This one you're going to have to take me at my word. The proof involves another rule that we need. I'll show you the proof real quick. It's a very short one. But you're not going to be able to fully understand it until we know this thing called the chain rule. But the idea, the general idea, and I'll show it to you, is that let's say we have y equals natural log x, and we want to know the derivative. We want to know y prime. Okay? So we don't know it right now, but we know any logarithmic equation can be written in exponential form. And the exponential form of this equation would be x equals e to the y. And so then what I can do is go, okay, I'm ready. I'm going to take the derivative of both sides of this equation. Now I'll look for some participation in the chat. What is the derivative of the left-hand side? What's the derivative of just x? Okay, it's just 1. Yeah. So this left-hand side is 1. Now, what do you think the derivative of e to the y is, if you'd have to guess? It's a good guess, Dylan. And that's part of it. The only issue is we're treating x as our variable. We're taking the derivative with respect to x, but we're differentiating e to the y. And y is a function of x. So we have to use this thing called the chain rule. You guys don't know what that is, but I will tell you this is how it works. You are partially correct, Dylan. It is e to the y, but then we say times y prime. Right? And so that's the chain rule. You guys won't understand that step, so I just need you to trust me that that is true. Now my whole goal is to figure out what y prime is equal to, right? So if I isolate y prime in this case, I get y prime equals 1 over e to the y. But I don't want my answer in terms of y. I'd like my answer in terms of x. But notice up here, what did we say that e to the y equals? E to the y equals x, right? So really what I have is that y prime equals 1 over x, which is exactly what we said the derivative should be. All right, I'll come back and redo that proof once we learn the chain rule, and it'll make a lot more sense. Or at least this one step here will make more sense. But yeah, derivative of natural log x is 1 over x. All right, we're almost done. All right, so f of x equals 7x minus 3 plus natural log x. Find f prime at 1. All right, so first let's find f prime at x. And so we'll just differentiate each term separately. What's the derivative of 7x? Seven. What's the derivative of 3? 0. Derivative of a constant is 0. What's the derivative of natural log x? 1 over x. So we have 7 plus 1 over x as our general derivative. So then f prime at 1 is just 7 plus 1 over 1, which is 8. And that is it.